Hello again and welcome. These are some of the shunts that have come out of the meters that I've damaged. You can see that their shape, size, and thickness varies quite a bit. You'll notice that some will have a crimp, like this one here, see right at the tip. And I'm assuming that's so they get consistency when they slide these into the board. Some of them have no crimp joint, and I'm not sure if they don't have maybe a fixture that sets the height when they put them into the board and solder them. As far as the materials, I'm not sure what they're using as well. So I've got a little fixture here, and I thought it'd be interesting to make some measurements with these. I think before we do that, I've got a couple of different pieces of wire. These are both Nichrome. So the smaller Nichrome, this is made by Omega Engineering. It's a part number NI80-032, and it's a Nichrome 80, so that's 80% nickel and 20% chromium. This has a diameter of 32 thousandths of an inch, or 0.8128 millimeters. The manufacturer specifies the resistance of this wire at 0.6348 ohms per foot, and that works out to 0.0529 ohms per inch. And Nichrome has a temperature coefficient of 0.13. So if I wanted to make a 1-inch shunt using this material, the resistance is equal to length times the specific resistance divided by the cross-sectional area. So if I calculate this out, the resistance for our 1-inch piece of this wire would be 0.054925 ohms. And you notice that's very close to the manufacturer's number of 0.0529. So the reason I'm calculating this is there's a table on the internet that I had found, and I just wanted to run through and see if some of these numbers make sense. So let's see if we can measure this. This is my 34401. This is not really accurate enough to make this kind of measurement, but we'll go ahead and see what we get with it. So you can see I've nulled out the meter, and we're just using a set of 4-wire probes. So you can see here what I've done is I've straightened up the wire a little bit, and I've attached the clips using a caliper to set the distance between the two. And this is currently what our meter's reading, so roughly 53, 52 milliohms. So it's fairly close to what the manufacturer specifies. Again, you can see I have my PC out. I have my Bryman meter, and that's connected up to my shunt. And again, this is a 1 millivolt per amp. And then over to the left, I have my power supply. This down here is just a ceramic block, because I'm sure that we're going to get things pretty hot. You can see I have a couple of clamps. So currently these clamps just have a couple of wires that go across to my shunt. And again, the Bryman's just looking at the voltage drop across the shunt, so this will be reading in amps. So for this first test, all I want to do is compare the PC against the Bryman. And we can see the PC is currently displaying 10 amps, and the Bryman is as well. And this is running closed loop right now. So what I'm going to do is increase this to 20 amps. And again, we can see our current is displaying 20.0 and 20.0 on the Bryman. I'll go ahead and increase this to 40 amps. And again, we can see our PC is displaying 39.9 or 40.0, and the Bryman is also displaying 40.08. This is at its maximum current. You can see we're displaying roughly 100 amps or 99.9 and 100.09 on the Bryman. Power supply is good for about 105, I believe. Oh, this is our top end right here, so about 102.3. So that should give you some confidence in the numbers that I'm displaying. And again, the reason for that is that I'm not going to have the Bryman attached for the rest of the testing. As you can see, I have a couple of clamps here, and there's some pretty hefty gauge wire attached to these, especially compared to our little Nichrome wire. And what I'm going to do is clamp our Nichrome wire in between these two, and I'm going to set that spacing for about 1 inch. I'll go ahead and tighten all this up. I'll double check. You can see the gap is pretty close to 1 inch right there. This is our 1-inch piece of Nichrome installed between the two clamps. I have a small thermocouple that's attached to the Brahman meter, and I'm currently putting 1 amp through the shunt. This display on the left is showing the resistance. Of course, I have all this cabling and our connectors and such that are installed, and we're not compensating for any of that. So currently we're displaying 0.069 ohms, and again we had calculated roughly 0.054 or so. So this is in the ballpark of what we would expect. So what I'll do now is I'll sweep the current from 1 amp all the way up to 25 amps, and we'll do that in increments of 1 amp, and I'll use a 5-second dwell at each level. And one of the things you'll notice is how stable the Nichrome is. You can see our temperature is already up to 54 degrees Celsius, and our resistance is just barely moving. See, we're already at 160 degrees Celsius. We're putting roughly 9 amps through it, and we are now at basically 73 milliohms. You can see our little piece of Nichrome is starting to glow cherry red. We're at 330 degrees Celsius now, and the resistance is still 72 milliohms. So we're all the way up to 650 degrees Celsius now, and the resistance is still 73 milliohms, and we're putting roughly 23 amps through it. Oh, it just broke. So it looks like we just got lucky and it happened to break at 25 amps. This wire is made by Pelican. It's also a Nichrome. You can see it's quite a bit thicker than the wire we just tested. This is actually 18 gauge instead of 20 gauge, so it's 40 thousandths diameter. And this is Nichrome 60s. Instead of being 80% nickel like this is actually only 60% nickel. And then it's a smaller percentage of chromium, and the rest of it is made up of iron, I believe. The specific resistance for this is slightly different than the Nichrome 80, and with it having a larger diameter, I had to use a little bit longer piece of this, and you can see we are roughly at 0.057 ohms right now, and I'm outputting between 2 amps at cycling and 3 amps. And again, you can see our thermocouple just resting up against the piece of Nichrome. And I'll run the same sweep as before. And this will be from 1 amp to 25 amps in 1 amp increments. You can see we are roughly at 108, 116 degrees, and the resistance is 0.049 ohms. You can see our Nichrome is just starting to glow red. We're at 300 degrees Celsius roughly. We're outputting roughly 22 amps, and the resistance is still 51.2 milliohms. This piece is not going to have any problem at 25 amps. There's our maximum. And you can see we're still at 51 milliohms, and we're all the way up to 370 degrees Celsius. So again, one of the reasons that you may want to use Nichrome for a shunt is because of its temperature stability. It also has a fairly high resistance, and that allows us to use a smaller piece of wire to create the shunt. Sure, a few of you are curious how much current it would take to open up this 40 thousandths diameter piece of wire. Let's just find out. So again, this is currently at 2 amps. We know it withstood 25. Let's just try it up at 30 amps. Seems to handle that just fine. Let's go to 40. You can see we're almost to 600 degrees Celsius right now. The resistance is still 52 milliohms or so. Let's try it at 50 amps. There. She just popped. But again, still quite stable. What's left of our 40 thousandths piece of Nichrome 60. So what I have now is just a piece of copper wire. I've just removed the insulation, and that's installed in here. I have a fair amount of length to this, and you can see we are at roughly 6 milliohms now. So you can see the resistance is quite a bit less than this Nichrome 60 was. with a longer and thinner piece. Unfortunately, the resistance of this wire is so low, I can't adjust the supply voltage low enough to get the current below 5 amps, it looks like. So what I'm going to do is we'll just start it off at 1 amp, and eventually the software will catch up to it. See, we're at 32 degrees Celsius right now, and it's still roughly 6.4 milliohms. You see, we've only changed to roughly 98 degrees or so, but the resistance was moving quite a bit. Let's just repeat this and we'll run all the way up to 50 amps. See if we can get the temperature up a little bit higher. Again, you can see we're at roughly 60 degrees Celsius and our resistance is starting to move. You can see our resistance is more than doubled now, and we're only at 150 degrees Celsius. So this is looking at the data I just collected. So this top blue line is our Nichrome 80, the green is our Nichrome 60, and you can see these are varying roughly maybe 6 milliohms. But if we look down here at our copper, that's 20 milliohms at that location, or roughly 4 times the amount of resistance. And that's what I was saying, is the temperature coefficient for copper is quite a bit worse than either of the two Nichrome wires. So recently I ran this Shunt KT6000, and again we can see this meter was rated at 20 amps. In the manual it states maximum measuring voltage drop, measuring range of 20 amps is 200 millivolts. And of course, with 20 amps flowing through this meter, it was nowhere near 200 millivolts. I think it was close to a volt or something. So currently all 5 of these meters are in series, and I'm putting through roughly 5 amps right now. So these meters don't have to be turned on to complete this circuit. You can see they're reading roughly around 5 amps. So I'm going to use the Bryman to measure the voltage drop across these meters. And currently you can see I'm looking at the voltage drop across this Tech Power, and it's roughly 160 millivolts. Let's look across Dave's Bryman. So you can see this one is about 140 millivolts. So Dave's meter is quite a bit better. Let's look at my Unity. This is 126 millivolts. It's looking at the AM510, and we're seeing 225 millivolts. Now you may think that this is going to be very high, but I doubt it. Let's have a look. 65 millivolts. So the lowest burden voltage of all the meters that are shown here. So let's take a look at a couple of these and see what the differences are. So let's start by looking at the UT61E by Unitrend. Of course, this meter's been modified quite a bit. So the first thing I've done is I've replaced all the split connectors with a machine type. This meter didn't originally come with this large HRC fuse, so I've replaced that. And I've also damaged this trace on a previous version of the 61E. And I scraped away some of the solder mask, and you can see I've laid down this wire, and then I've covered that up with Corona dope. And that's the reason this meter has such a low burden voltage. Again, this has a total voltage drop at 5 amps of roughly 115 millivolts. And we can see across the fuse caps it's roughly 44 millivolts. And across our shunt it's about 43 millivolts or so. If we look at the Amprobe AM510, you can see the drop across this fuse, looking at the two end caps, is almost 83 millivolts. So that's about double the drop of the fuse that I selected for the UT210. You can also see this meter is using split style connectors. So if I'm measuring from the top of that connector over to the fuse cap, you can see it's reading almost 27 millivolts just for that. So I think if they would have used a larger fuse, better connectors like what I've done with this UT61E, it would have really helped the burden voltage for this meter. So what's the secret for this little freebie meter? Well, you guessed it, it doesn't have a fuse. And without that fuse, there's nothing there to drop. So the only thing that we really have in here is this shunt. So that's why the burden voltage of this meter is so much better than these others. So it doesn't mean that this is a better meter than the other ones. It just means they decided to save some money and not use a fuse. So this Unity UT61E had the lowest burden voltage of the meters that I just showed you. You can see I'm now putting about 10 amps through this meter, and it's currently dropping about 254 millivolts or so, far exceeding the 200 millivolts that was called out by that Shunt test meter. So I don't think hitting 200 millivolts with a meter like this is trivial. Again, this has the large style HRC fuses. You can see where I've increased the trace capacity quite a bit, and this meter is still nowhere even close to hitting that number. So I think it's about time we can look at some of these shunts. So I've chosen these two in particular. This top one comes out of the Radio Shack 200087, and this bottom one came out of the Shunt Test ZT102. Also, I'd like to mention that this is that Nichrome 60 wire that I had looked at, and I looked up the specifications for this, and this is 58% nickel, 15% chromium, 1.5% silicon, and then the balance is made of iron. And again, we talked a little bit about the temperature coefficient and how stable it is for this Nichrome, and I'd mentioned that there's other materials that could be used for shunts that actually have a higher resistance, and they also have a better temperature coefficient. And one of those materials is called manganese. Manganese is 12% magnesium, 2% nickel, and 86% copper. So looking at the shunt out of the Radio Shack meter, I measured the diameter of this as 0.072, and that would be 13 gauge wire. This is approximately 3.2 inches long. If I go through the same calculations that I showed for the Nichrome wire, except using a specific resistance for the manganese, this works out to a resistance of 0.0149175. This shunt out of the Shunt test, this has a diameter of 0.039, and again compare that with the Radio Shack at 0.072. This has a length of 1.2 inches versus 3.2 for the Radio Shack. But again, if I work the calculations for this, this also works out to a resistance of 0.018. So these two actually have the exact same resistance for that type of material. Now, why would they choose something that's a little higher resistance? Well, if we look at the percentage that's actually buried inside of the circuit board, some of this isn't even going to come into play. Some of this will actually stick through the circuit board and no current flows through it. So I believe that they picked the numbers slightly higher. So let's try to measure these and let's just see what we get. So you can see our Radio Shack shunt attached to our HP34401A, and we're reading roughly 17 milliohms. Now again, this is really pushing this meter, so I don't carry a lot of stock in this, but it does say that we are probably in the ballpark, so it does make me believe that they're using manganese, at least for this shunt. And here you can see the smaller shunt from the ZT102, and again it's about 16.6, or call it 17 milliohms. So these two shunts actually have the same resistance. So even though this is a lot bigger, thicker, much smaller, thinner wire, same material, I think it's both manganese. So I think that that's a fairly common material for the meters, whether they're made very cheap and inexpensive like the ZT102 or a little higher end like the Radio Shack. Here you can see I've installed the ZT102 shunt. Basically I've clamped it at the height where the solder had wicked up on the shunt. And you can see I'm reading roughly 0.01 ohms. And that would make sense that they'd use a value like that for a shunt. So let's go ahead and we'll install our Radio Shack shunt. And you can see again we are about 10.8 milliohms. So very close to this ZT102 shunt. So again, I'm pretty happy with the calculations. I think we're in the ballpark. I think both of these shunts are basically a 0.01 ohm resistor, and I believe the material that they've used is manganese. So I'm all set up to finally run the test. You can see I've changed out my Bryman BM869S for the X-Tech EX540. The reason I'm using this particular meter is it has a wireless connection going back to the PC, and I can log that data using LabVIEW. So the same software that's controlling the power supply will also be recording the data off of this meter. So currently you can see I'm putting roughly 3 amps through our shunt, and it's at 33.7 degrees Celsius. It's slowly cooling down. That's because I had this thing actually heated up for a little bit. What I'm going to do is run a sweep, and this is how I'm going to be testing our shunts. So we're going to start off at 3 amps, and I'm going to step the current by 1 amp up to 100 amps until the shunts fail. And we'll just collect the temperature, the resistance, the voltage drop, the power that's dissipating, and the current all into a file, and then we can post-process that information. So our temperature is about 720 degrees Celsius now. We are dissipating almost 100 watts with about 50 amps of current flow through it, and we are still at about 44.3 milliohms. Oh, and you can see our shunt just melted, and it's starting to cool, obviously. So this is basically what we're going to be doing with our shunts. I've made up a little spreadsheet for the shunts that we're going to run. The one in the upper left is our Radio Shack shunt, and then this one is from the ZT102. And again, these two have the exact same resistance, made out of the same material. So why would a company do this? Well, obviously if you're removing materials, it's going to be quite a bit cheaper. There's a downside to removing material though, and that's that the watt density for this little shunt is going to be much higher than it is for this large shunt. I've gone through and I've calculated the watt density for each one of these shunts. We can see for the Radio Shack shunt, I calculate a watt density of 2.06 watts per inch squared. For the Currrent ZT102, it has a watt density of 12 watts per inch squared. You notice the one just above it is also 12 watts per inch squared. That happens to be our little Centec 98025. This is the shunt out of the little free Harbor Freight meter. So it shouldn't be too surprising that these have the least amount of materials, because these are the two cheapest meters out of this whole group. What's interesting is if you look at the first two, the Radio Shack and the one next to it, you can see comparing the watt density between the two, there's about 1 watt per inch squared difference. But just looking at the two, you wouldn't think that that would be the case. But when you look at the measured resistance, notice that this shunt has half the resistance of the Radio Shack shunt. It also has a slightly smaller diameter. When I was looking at the burden voltage for the few meters that I checked, the UT61E that I had modified was the best one out of the group. This is looking at the voltage drop for each of these shunts based on a 10 amp current flow through them. And you can see the Radio Shack is about 149 millivolts. Some of these will get down to about 88, 89 millivolts. Looks like the worst one is this one here at about 185 millivolts. And that's the Hold Peak H760H. Of course, that one Currrent meter claimed that they could do 200 millivolts of burden voltage at 20 amps. But when you look at all these shunts, you can see that we've pretty much eaten up all that margin at 10 amps just for the shunt. So I'm going to start this testing with the shunt out of the Radio Shack 20087. This had a measured diameter of 0.072 inches. This is a 13 gauge. It's roughly 3.2 inches long. It has a watt density of roughly 2.0 watts per inch squared. So I'll be running all these shunts the same. Again, we'll be starting off with 3 amps. I'll be incrementing by 1 amp every 5 seconds. The top graph will be displaying the temperature at the shunt, and the yellow will be displaying the current through it. So here we go. This will be the Radio Shack shunt. Well, that is impressive. That was 100 amps flowing through that shunt, and it would not open up. You can see it has a very small dent in the tip of it, right where the thermocouple was resting. That might have gave it just enough cooling to save it. Next up, we have the shunt out of our BK2705B. This had a diameter of 0.064 and a length of 1.5 inches. I have a calculated resistance of 8.8 milliohms and a watt density of 2.9 watts per square inch. You notice this shunt starts out a little high. It's because it's got half the resistance. I can't drop the supply voltage any lower. Well, again, it looks like we didn't damage it. And you can see it's melted down a little bit at the top, but it didn't break in two. So next up, I have one of the shunts out of the SEM meters. This one's out of the DT932. This has a diameter of 0.063 and it's 1.5 inches long. It also has a calculated resistance of 0.00885. It has a watt density of 2.9 watts per inch squared. So again, looks in pretty good shape. Next up, we'll have a very similar shunt. This is out of the SEM DT9962. It has the same diameter, same length, same calculated resistance. You can see it also measures roughly the same resistance on our test jig. So again, the shunt looks pretty good. Next up, we're going to be running the one out of the Klein MM2000. This had a measured diameter of 0.064 inches. It has a total length of 2.9. So again, the calculated resistance for this is 17 milliohms. And you can see we're in the ballpark here. You can see it was definitely dissipating some power. It started to melt, but it's still intact. Next I have the shunt out of the UT61D. It has a diameter of 0.063 and a length of 1.6 inches. It has a resistance of 9.4 milliohms. And you can see it's reading roughly 6.6 milliohms on our test jig. I believe this is the solder that was wicked up on the edge of this. Again, still didn't break. Next up, I have the shunt out of the Vichy VC99. This had a diameter of 0.063 and an overall length of 1.3 inches. Calculated resistance was 76 milliohms. So again, it looks in pretty good shape. This will be the shunt out of the Unity UT61E. This was a 57 thousandths diameter. It has a length of 2.3 inches. See, the color is slightly different for this, and that's because the watt density of this is quite a bit higher. You can see it's 4.15 watts per squared inch. So our UT61E is our first shunt that did not survive. Next I have the shunt out of the Hold Peak 760H. This has a diameter of 0.051 inches and an overall length of 2 inches. The calculated resistance is 0.0185, and we can see it has a watt density of 5.8 watts per squared inch. It's interesting, you can see it actually broke up here. So there's the shunt out of the Hold Peak, not surviving. This will be out of the Maztec MS8237. This has a 46 thousandths diameter and a 1.5 inch length. The calculated resistance for this was 17.9 milliohms. And the watt density was 8.4 watts per square inch. can see again it melted in the center, but the brake is actually away from that. Next we'll have the shunt out of the little Harbor Freight free meter. You can see where they've crimped it to adjust for the current. Very cheap way to produce it. So again, this is out of a Centec 98025. These are available from Harbor Freight for free. The diameter of the shunt is 39 thousandths. The length is 1.2 inches. This has a calculated resistance of 18 milliohms. The watt density is 12 watts per squared inch. So by far the highest so far. There's the shunt out of the Harbor Freight meter. I've saved the best for last. This is the shunt out of the Currrent ZT102. This is pretty much the same as the Harbor Freight meter. You can see it has the same diameter and the same length. It's just bent slightly different. So the watt loading is the same. And there you have it. That's the shunt out of the ZT102. So again, this is looking at the shunts that I just ran. Several were destroyed. Let's go ahead and we'll have a look at the data that we just collected. So this is looking at the voltage drop across the shunts. This area here in the lower left is 0 volts. At the very top of the screen is about 6.5 volts. So what you see happening at this point, for example, is where the shunt is opened up. This is looking at current. Because I'm closing the loop on current, all the graphs will actually overlay. This is looking at the power dissipation in each shunt. And this starts out at 0 watts, and at the peak is about 182 watts. And this is looking at the temperature. So this blue trace that's kind of an oddball is actually the Nichrome wire. Let's go ahead and we'll zoom in just a little bit. This is again looking at the voltage drop. You can see there's a group here, and of course the voltage drop across our Nichrome wire is quite a bit higher. But now you can see the current through all of these basically lines up. And again, this is looking at the power dissipation, and this is looking at resistance. And again, remember I was saying that the temperature coefficient for Nichrome, even though it's pretty good, it's not as good as what they'll typically use for a shunt. So let's just turn off that trace. Now you can see the resistance values for all the different shunts. And you can see how flat these are. So this is looking at a zoomed in view of the ZT102 shunt. You can see it starts off at about 9.9 milliohms, and it remains fairly flat. It gets up to about 10.01 milliohms, and then it slowly starts working up, and then we have this sharp knee. If we look at the temperature at that point, you can see right here we're at about 650 degrees Celsius, and we can see too that the temperature is starting to increase quite substantially. I believe this is the point where the material starts to melt. Doing a quick search on manganese, we can see that the melting point is roughly 960 degrees Celsius. And you can see I've heated it all the way to about 1056 degrees Celsius. And this is roughly where it opens up at. Let's just compare that with the Centec meter. And again, we can see at right about that same point something happens with resistance. It starts to increase and then it drops dramatically. And I believe that's because these wires are quite a bit thinner. Let's pick something that's a little bit thicker. For example, if we look at the Vichy, which is quite a bit thicker, so now we don't have the wire melting down, we can see that it's very stable. Looking at the blue trace, this is out of the Unity UT61D. This is out of the 61E. The D model is using a 5 milliohm shunt and the E is using a 10 milliohm shunt. But again, you can see the temperature coefficient for the two is basically the same. This is looking at all the meters with a 10 milliohm shunt. And you can see that the profiles all remain basically the same. This is the hold peak. And again, what I suspect is happening in this area is where the hold peak is starting to melt. If we look at the temperature for each of these, again, we can see this dramatic rise for the hold peak. Unfortunately, you can see where I was collecting the data for the Maztec shunt. That's this gold trace here. The SEM meter stopped transmitting the data, or I lost the link. And that's the downside of using a handheld meter to do your data collection. But again, looking at the power dissipation curves for all of them, they're basically the same. And looking at the voltage drop for all, they're basically the same. And again, this is looking at all the 5 milliohm shunts. This includes the BK Precision, the two SEM meters, the UT61D, and the Vichy VC99. This is looking at the power dissipation. And again, this is the resistance. And again, we can see the BK Precision starts to change in this area here. And so does our UT61D. I've zoomed into the 0 to 20 amp area, and I have all the shunts currently selected. And if we look at the resistance, we can see they're now all very flat. So this is in the normal operating range of the shunts. Well, I think that's going to be it for this video. You can only ramble on about shunts for so long. Looks like there's over 2,000 of you following this channel now for some strange reason. Haven't forgotten about you. Unfortunately, Dave has not released his new meter just yet. And that's what the majority of you would like to see ran. So I have no idea when he's going to actually release this meter. So I started looking at buying the runner-up meter, which would be a Gossen. And so far I haven't found anything that I actually like. If I'm going to buy a meter with that expense, you know I'm going to buy one that I actually would use around here. So I was looking at their energy version or something, but I saw Dave's video on it and I just basically wasn't impressed. Seeing that little resistor tacked on there, the build quality didn't look all that great to me. I downloaded the manual for the extra. The meter looks okay. The manual talks about some accessories that they offer for it. Whereas a WS20, I believe it is, which is supposed to harden the front end of the meter so it can survive a bigger transient. But I can't find any more information about that accessory on their website. So I think what I'm going to do is just write them and see what they have. Maybe tell them what I'm doing and see if they think that the meter would even survive these tests. So it's going to be a little while before I run a real good meter. So just stay tuned for that. And I think that's going to be it. So till the next meter. Later.